Hello, welcome to our first lesson of Chapter 3, Exponential Functions and Their Graph. Now what this unit will do is it will take us exclusively on a path through exponential problems and functions and logarithmic functions and problems, or problems and functions, and how they interact with each other. We're going to begin by defining exponential functions. An exponential function f with the base of a is denoted by f of x equals a to the x power, where a is greater than 0 and a is not equal to 1 and x is any real number. In the past we've dealt with any equation where we've just said, y equals x squared, y equals x to the third power. Now we're dealing with an equation where instead of having an exponent that's a number, the variable is in the exponent. Let me give you an example of evaluating some exponential functions. Now for these, you would put these in the calculator. Exponential functions, logarithmic functions, we do a lot with the calculator because it's just logical to do so. I'm not a fan of calculators. If there's a reason to not use a calculator, I won't use one, but in this case, it's just kind of superfluous not to use one. It's kind of stupid. Okay, so if I wanted to evaluate 2 to the x power and wanted to evaluate it for negative 3.1. So what I'm doing is I'm plugging this equation, or this variable, into that function. So I would raise 2 to the negative 3.1 power. So what I've given you here is the function value, the keystrokes that you would type on a calculator, and what the answer would end up being. So I would type 2. Now this symbol right here we call the caret. That symbol is going to become a very much used symbol this year in this class, this chapter. You will use it quite a bit. That's basically raise it to the power of. Technically, when you have the x squared button on your calculator, that's caret followed by a 2. In this case, we're going to take 2 and raise it to the negative 3.1 power. Sometimes some people like to put in parentheses around that. The answer that you get, so we do 2 to the negative 3.1, that equals 0.1166291. 2 to the negative pi power, 2 to the negative pi, punch it in the calculator, 0.1133147. And 0.6 raised to the 3/2 power. 0.6 raised to the 3/2 power is going to be, it'll kind of look like that, and the answer would be 0.4647580. The only real skill that you're using here is that you're plugging it into a calculator. Click, 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 enter. Now, we're going to look at some of the graphs here. So what is the graph of y equals a to the x? What is the parent functions, or what is really the graph of raising some number to the x power? In the same coordinate plane, we're going to sketch the graphs of y equals 2 to the x power and y equals 4 to the x power. What I've done here is I've given you the graphs and I've given you the table. So when I raise 2 to the 0 power and 4 to the 0 power, right here in the center, I just get 1 and 1. So that's this point right here. But notice how with the larger base, the larger the base is, the more steep it goes. Because when I raise 4 to the first power, I get 4. But if I raise 4 to the second power, I get 16. Whereas with 2, if I raise it to the first power, I get 2. And 2 to the second power is 4. So you can kind of see the interactions here that with an exponential graph, your graph will continue infinitely in the direction of negative infinity, but notice that it never goes below 0. It never ever goes below 0. And it will continue infinitely up in that direction. So it goes from a very slight down on the right, from left to right it goes very, very close to the x-axis and then goes up drastically. It goes up what we would call exponentially. Now, same graphs, only now raised with a negative x power. Notice what happens is they're flipped. So now, when I raise it to the negative x power, it basically causes it to reflect across the y-axis. So now instead of 2 to the first power being 2, 2 to the negative first power becomes 1/2. And instead of 2 to the negative 1 on the original one being 1/2, in this case, because of that negative flips the sign of any x value that I plug into the equation, and so it causes it to become larger going up in the opposite direction. So the difference between these two sets of functions, they're the same numbers, it's just notice that up here they're flipped with these over here. So going -3 on the first set of graphs corresponds to +3 on the second, because your x values are switched. But the y values that correspond switch with them. It is a perfect reflection across the y-axis. So to compare the graphs of exponential functions, for y to the equals a to the x power, you would say that when a is greater than 1, and your exponent is positive, it has an infinite domain. The range is bounded by 0. It gets as close to 0 as possible, but notice this right in here. The fact that the parenthesis is there means that it will get as close to 0 as possible, but it never reaches 0. It is said it will have a y-intercept of 0, 1, the parent function, and it is said to be increasing, meaning when it goes from left to right, y is going up. The x-axis is the horizontal asymptote. You'll recall from when you learned about rational functions that you would have these asymptotes that would be vertical or horizontal or slant asymptotes that the line would try to get as close to as possible but would never cross. And it is continuous in that it has no breaks. It doesn't have any holes, it doesn't have any pieces. It's one continuous graph from negative infinity to positive infinity. Now on the right we have the attributes of y equals negative, or it's a to the negative x power. Same domain and range, same y-intercept. The only difference between the two is that it is said to be decreasing, meaning that as it goes from left to right, and I'll put an arrow in there, from left to right, y goes down. As it goes from left to right, y goes down. You still have a horizontal asymptote at the x-axis, and it is still continuous. Now, a property that is very key is called the one-to-one property. You learned this in Algebra 2, but this property is going to play a very heavy role in this section. The one-to-one property states that if two exponential problems end up having the same base, I can set the exponents equal to each other. And what I mean by that is, let's take a look at 9 equals 3 to the x plus 1 power. What I want to see if I can do when I use a one-to-one property is I want to make this resemble this. So is there any way that 3 to some power equals 9? Well, I know that 3 squared equals 9, so I can rewrite it as 3 squared equals 3 to the x plus 1. Notice my bases are the same, so my bases drop to be 2. That was a horrible 2. 2 equals x plus 1. Subtract 1 from both sides, and x equals 1. So what that basically says, if I were to plug it back in to test it, 3 to the x plus 1, which x equals 1 is my answer, if I were to plug it back in, I'd get 3 squared, which is 9, which is precisely what I was looking for in the first place. So with a one-to-one property, one thing I can do to try to solve some sort of exponential equation is to basically try to set both sides so that they're the same base, And if I can find that same base, then I'm good to go. I just drop the bases and equal the exponents. Now, another thing we learn about is called the natural base, or the number e. And I've given you a graph up there that you're going to want to copy down, and that is basically the graph of y equals e to the x power. So an exponential graph with a base of e. E is a natural number. We still don't fully understand it. It's one of the beautiful mysteries of nature, that of the universe, we don't completely understand. There is a recurring number that keeps popping up across multiple studies, multiple disciplines, multiple subjects, and that is this natural number. It's an irrational number of 2.718281828, so on and so forth. And so for that sequence of numbers, we prescribe the letter E. This has popped up so many times over the past 2 to 3 centuries, even maybe 4 centuries. It pops up in so many disciplines that it has become known as the natural number, because it just appears in nature. So if I were to want to evaluate the function, we're basically evaluating y equals e to the x power, the natural number raised to some power. I can do it with a calculator. I am not going to try to do that by hand. There are so many better things I could do with my life. I could go eat a donut. I could go bang my head against a wall. I could go flap my arms outside and try to fly. Those are much better things than trying to solve out a natural base exponent. So to plug it into a calculator, so I would solve it for -2. So I would just say e to the -2. And on most calculators, there is this button, e to the x. I punch that button, and then the next thing I punch in is the exponent, and I press enter. So e to the -2nd power is 0.1353353. To the -1st power is 0.36789,794. To the 0.25 power, 1.2840254. And to the -0.3 power, 0.7408182. So all I have to do when I have an e to the certain number, type the e button on the calculator, type the exponent, enter, and I'm done. Very simple process. So to graph some natural exponential functions, I've sketched the graph here. We have 2 times e to the 0.24x and 1 over e to the -0.5x. Now remember, e is a number. E is not a letter, e is a number. One of the key mistakes that I will see students make when we talk about this is that they will think of e as it being a variable like x. E is not a variable. Okay, remember e, the number e, is 2.7 blah, 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 on and on and on. Okay, so what you're effectively doing is you're saying 2 times the number e raised to the 0.24x power, and 1/2 times e raised to the -0.58x power. Notice on the one on the left, okay, when I plug in x equals 0, it just becomes e to the 0 power. Any number to the 0 power is still 1. Even e. Okay? This is my graph, and these are some of the points. This is what it looks like. So on the one on the left, it'll take a more steep exponential curve up because of the 2. Whereas on the one on the right, it flips because of this little negative right here that causes it to flip, and as a result, it decreases rather than increases. It increases to the left rather than increasing to the right. And that concludes this lesson.